Alright, in this video we're going to go ahead and calculate what's called the Dilogarithm function. Now the Dilogarithm function is actually a part of a family of functions called polylogarithms. And this is a particular case where we're having a square in the denominator of this infinite series. And this is the sum, as n ranges from 1 to infinity, of z to the n over n squared. Now the absolute value of z is less than or equal to 1, so therefore this is defined over the complex unit circle. And ideally, we have the case where z is not equal to 1, because under that condition, this is not absolutely convergent. It is instead conditionally convergent under what's called the Riemann Zeta function. And you should be able to convince yourself that we do indeed get the Riemann Zeta function when we evaluate z to be equal to 1. In this particular case, we're going to evaluate the Dilogarithm at 4 different values, namely the Dilogarithm of 0, the Dilogarithm of 1, the Dilogarithm of -1, and the Dilogarithm of 1/2. As you can see here, the absolute value of all of these real values is less than or equal to 1. So, let's go ahead and just begin. We'll start with the Dilogarithm of 0. Now this should be pretty simple because all we're going to do here is just plug in our value of 0 for z. So this is a sum from n equals 1 to infinity of 0 over n squared. But of course that just gives you 0 plus 0 plus 0 continually. So quite trivially, this equals 0. And this is our first value. So we can go ahead and cross out the Dilogarithm of 0. That's our easiest one. These are going to get progressively harder as we go down the list here, and we're going to rely on more techniques as we go down the line here. So let's go ahead and evaluate at 1. So here we have the Dilogarithm of 1. Now we can go ahead and write out our series. I think we're going to do that for all of our values here. So this goes from 1 to infinity. As usual, we're going to have that series all throughout here, this particular infinite series operator. In this case, we're plugging in 1 for z, but 1 to the any power n from 1 to infinity is just equal to 1. So we get 1 over n squared. Now, if you've gotten far enough into mathematics where you're computing dilogarithms, this infinite series should be ringing bells for you. Because let's consider if we have the series, as n goes from 1 to infinity, of 1 over n to some value k. Well, this is just equal to the Riemann Zeta function evaluated at k. And we'll write that out here. This is the Riemann Zeta function. Now, as we recall here, when we have z equals 1, this becomes conditionally convergent under the Riemann Zeta function because here we're evaluating k at 2. So this is the Riemann Zeta function evaluated at 2. But that's also called the Basel problem, and that has a well-known solution of pi squared over 6. So that goes ahead and gets rid of the Dilogarithm of 1. We've calculated that. We're roughly halfway through, but you'll see that these take a little bit longer to calculate. Now, these Dilogarithms appear a lot in in-loop calculations, electron-positron scattering calculations, radiative correctness procedures, thermodynamic ansatz, things of that nature. When you're doing these types of calculations, you're going to get the Dilogarithm, and more namely the polylogarithm family of functions in general. This is just one of the most common ones that pop up in quantum field theory and in physics in general. So let's continue on now with the Dilogarithm of -1. Okay, so let's go ahead and plug that in here. n ranges from 1 to infinity of, well, now our z is negative 1, so we have negative 1 to the n power over n squared. Now this looks very close to the Riemann zeta function, but actually it's more closely related to a function that itself is related to the Riemann zeta function, and that's called the Dirichlet eta function. But this is not quite the Dirichlet eta function. We would have to have an n plus 1 right here for this to be the Dirichlet eta function, evaluated at 2. So if we have a series from 1 to infinity of negative 1 to the n plus 1 over n to some value k, this equals the Dirichlet eta function evaluated at k. We'll write that out. The Dirichlet eta function. Now, to get an n plus 1 up here, we can just take out a negative 1 from the numerator. So this gives us negative the infinite series of negative 1 to the power of n plus 1 over n squared. Now we have the case where k is equal to 2. This is equal to the Dirichlet eta function. Or more specifically, let's not forget this negative sign here. That's easy to forget. Negative the Dirichlet eta function evaluated at 2. So now that we have that, how do we calculate the Dirichlet eta function? Well, notice the similarities between these infinite series, namely the Riemann zeta function series representation and then the representation of the Dirichlet eta function. These are very similar except for the factor of that numerator there. But we have a relational formula between the Dirichlet eta function and the Riemann zeta function. So if we have the Dirichlet eta function evaluated at some value k, this is equal to 1 minus 2 to the power of 1 minus k times the Riemann zeta function evaluated at k. But we have the case where we're evaluating this at 2, so let's plug that in. That's a j, not an eta. So we have the eta of 2 is equal to 1 minus 2 to the power of 1 minus 2, but 2 to the negative 1 is 1/2, so 1 minus a half is a half. So we get 1/2 the Riemann zeta function evaluated at 2, and it was just pi squared over 6. Pi squared over 6 times a half is just pi squared over 12. But notice here we have a negative sign. So the dilogarithm of negative 1 is equal to minus pi squared over 12. And that gets rid of this problem right here. So that's pretty neat. Let's move on now with the dilogarithm of 1/2. Writing out the series here. N ranges from 1 to infinity as usual, but now we plug in 1/2 for z. Over n squared. Okay, well, what can we do with this here? Well, let's go ahead and make this look nicer. We don't want a fraction in a fraction, so let's write this as the series as n ranges from 1 to infinity of 1 over 2 to the n times n squared. Now you notice this is a bit similar to the Riemann zeta function, but we have this 1 over 2 to the n, kind of like a flip. We have a 2 to the n and then an n to the 2. So we're going to expect maybe a factor of pi squared over 6. And that is accurate, but we're going to expect ourselves to subtract from that some type of arbitrary constant, perhaps in terms of logarithms, since this is a generalization of logarithms. And that's exactly what we get when we consider the digamma functions, or excuse me, the dilogarithm functions reflection formula. So if we have the dilogarithm of some value x plus the dilogarithm of 1 minus x, we can actually compute this quite easily because we do indeed get this factor of pi squared over 6 from this 1 over n squared minus some arbitrary constant. But what's that arbitrary constant generated by? Well, it's the natural log of x times the natural log of 1 minus x. We're now wanting to figure out what the dilogarithm is of 1/2, so we can plug in 1/2 for x here. So the dilogarithm of 1/2 plus the dilogarithm of, well, 1 minus a half is just 1/2, so we have another 1/2 here. And this equals pi squared over 6 minus the natural log of 1/2 times the natural log of 1 minus a half, which is 1 minus a half is a half, so we have another natural log of 1/2 here. And that's what we're left to calculate here to get our final answer. Of course, we're going to have 2 times these functions, so we'll have to divide through by 2 in order to isolate the dilogarithm of 1/2 to get our solution for this problem right here. So let's do that. Right here we have dilogarithm 1/2 plus another of those, so that's 2 times the dilogarithm of 1/2. And that equals pi squared over 6 minus, now what can we do with these 1/2? Well, 1/2 is just the same thing as saying 2 to the negative 1 power. So let's open up a parentheses here and write out the natural log of 2 to the minus 1 power times the natural log of 2 to the minus 1 power, close parentheses. Now, the exponent property of logarithms allows us to take this negative 1 and drop it in front of the natural logarithm. So this equals pi squared over 6 minus, open up parentheses, and then we have a minus sign in front of both of these, so we have minus the natural log of 2 times another minus natural log of 2 from this one here. Now, that just equals pi squared over 6 minus the natural log of 2 quantity squared. Now that's pretty nice. So we now just divide through by a half, or divide by 2 across the entire equation here to find the solution for this. So 1/2 times pi squared over 6 is just equal to pi squared over 12. Then we have a minus sign, and then we have the squared natural log of 2 divided by 2. And that's our fourth solution, finalizing our exercise.